by Maguire Lee. All sounds originate in the vibrations of material objects. Compressions are pulses of compressed air, while refractions are pulses of low-pressure air. As the source of sound vibrates, a series of compressions and refractions travel outward from the source. Sound must have a medium in which to travel through, such as solids, liquids, and gases. It cannot travel through space, for there are no molecules for it to hit against. Solids and liquids are better conductors of sound because it is much denser than gas. This allows the sound to travel faster and clearer. The intensity of sound is proportional to the square of the amplitude of a sound. Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a psychological sensation sensed in the brain. A subjective impression of frequencies is called pitch. Average person can hear around 20 to 20,000 hertz. Sound waves below 20 hertz are called infrasonic, while sounds above 20,000 hertz are called ultrasonic. Vibrations. The speed of sound in a solid material depends not on the material's density, but on its elasticity. Elasticity is the ability of a material to change shape in response to an applied force, and then resume its initial shape once the distorting force is removed. The speed of the sound in a material depends on the material's elasticity. When any object composed of an elastic material is disturbed, it vibrates at its own special set of frequencies, which together form its special sound. Its own special set of frequency is called a natural frequency. Forced vibrations occur when an object is made to vibrate by another vibrating object that is nearby. Sounding boards are an important part of all stringed instruments because they are forced into vibration and produce a sound much louder than the strings alone can produce. Resonance is a phenomenon that occurs when the frequency of a vibration forced on an object matches the object's natural frequency, and a dramatic increase in amplitude occurs. Sound interference. Sound waves, like all waves, can be made to interfere. The crest of a wave corresponds to compression, and the trough of a wave corresponds to a refraction. In both cases, when the crest of one wave overlaps the crest of another, there is a constructive interference and an increase in amplitude. When constructive interference occurs with sound waves, the listener hears a louder sound. Then destructive interference occurs, the listener hears a fainter sound or no sound at all. When destructive interference occurs, however, there is usually enough reflection of sound to fill in the cancelled spots. Distortion inference is how noise-canceling headphones work, due to its canceling waves reaching the earphones. As seen in this diagram, it sends out opposite wave um, crests and troughs to cancel out the sound for the listener. When two tones of slightly different frequencies are sounded together, a regular fluctuation in the sound of the combined sounds is heard. The sound is loud, then faint, then loud, and so on. This is called the beat. So as you can see here, this is where the beat would be heard due to an increased amplitude, and here there could be some canceling of sound, causing the sound to get quieter, causing a beat. Light waves. In 1905, Einstein published a theory explaining the photoelectric effect. According to this theory, light consists of particles called photons. Photons are massless bundles of concentrated electromagnetic energy. Scientists now agree that light has a dual nature, part particle and part wave. This can also be proved by the way light is affected by gravity. Stars' light can be bent by our sun's gravitational attraction, causing it to appear in the sky in one position when in reality it is somewhere else. Speed light is distance over time, and so overall it can be calculated to approximate or average 300,000 kilometers per second. Light traveling in a vacuum is a universal constant no matter the speed of the object emitting light. The distance light travels in 1 year is called a light year. Because light does not travel at an infinite speed, when looking at anything, you are looking at it from the past. If a star is 1,000 light years away, you're looking at it as if it was 1,000 years ago. Now, electromagnetic waves. Electromagnetic waves, light is energy that is emitted by accelerating electric charges, often electrons in an atom. This energy travels in a wave that is part electric and partly magnetic. A wave like this is called an electromagnetic wave. Light is a small portion of the electromagnetic waves. The electromagnetic spectrum consists of radio waves, microwaves, infrared light, ultraviolet rays, X-rays, and gamma rays. The lowest frequency of light we can see with our eyes is red, the highest being violet. Waves from the electromagnetic spectrum that are lower frequencies than the red is called infrared. Heat lamps give off infrared waves. Electromagnetic waves of higher frequency are called ultraviolet. Now, how a material reacts in the electromagnetic waves depends on the frequency of the light and the natural frequency of an electron in the material. The natural frequency of an electron depends on how strongly it is attached to a nearby nucleus. Light passes through materials whose atoms absorb the energy and immediately re-emit it as light. Materials that transmit light are transparent. Electrons and gas have a natural vibration frequency in the ultraviolet range. Because of this, when ultraviolet rays shine on glass, they cannot pass through. Because of this same natural frequency, resonance occurs, and instead it turns into energy, which then can be seen as heat, or you can feel heat on glass. However, when the electromagnetic wave has a lower or higher frequency than the natural frequency of the electrons in the material, this will cause the electrons to be forced into vibration with smaller amplitudes, causing, instead of heat to be transferred, but to transmit light through the material. This is why glass lets light pass through. When light is re-emitted, such as in glass, water, or diamond, the speed of which light is traveling while in the material is lower than the original 300,000 kilometers per second. It gets slower due to the medium in which is in slowing down the speed. However, once it re-emerges from the material, it continues at its original speed. Materials that absorb light and do not transfer light are called opaque. In opaque materials, any coordinated vibrations given by light to the atoms and molecules are turned into random kinetic energy. Metals, however, are also opaque. The difference between metals and things such as wood is the outer electrons of atoms in metals are not bound to any particular atom. They are free to wander with very little restraint throughout the material. That's why metal conducts electricity and heat so well. So when light shines on a metal and sets these free electrons free, the result is a reflected light back, which is why metal is shiny. A thin beam of light is called a ray. When light shines on objects, some of the rays may be stopped while others pass through in a straight path. A shadow is formed where light rays cannot reach. There are abscences of light. However, most shadows are somewhat blurry. A blurry shadow is called a penumbra. A penumbra appears when there is some light blocked by the object, but parts around the edges of the shadow is filled in by other sources of light, causing it to become fuzzy. A full shadow with no blurriness is called an umbra. Polarization. Light travels in waves in transverse and not longitudinal. This can be demonstrated by the phenomenon of polarization. Light is able to pass through a pair of polarizing filters when their polarization axes are aligned, but not when they are crossed at right angles. If this occurs, no light will be able to pass through due to the angles at which light travels to be blocked in all directions. Light that reflects at glancing angles from non-metallic surfaces such as glass, water, or roads vibrates mainly in the plane of the reflecting surface, so glare from a horizontal surface is horizontally polarized. This is the reason why snow goggles block horizontal wavelengths to block reflections off the white snow. When you click send on a messaging app, you are sending instructions to your mobile processor via tiny copper wires on a printed circuit board in your smartphone. This process of sending is using electrical impulses, which are electrons flowing along potential differences. The process of transferring the electrons flowing through the radio waves is by using an antenna. It takes in electrical impulses and produces radio waves. These waves pass through certain materials and even go around corners. Electromagnetic waves are basically the fluctuation in the electromagnetic field. So to produce radio waves from an antenna, it must create fluctuations in the electromagnetic field. To create this fluctuation, you need electrons to move around in a conductor. The act of radio wave synthesis is much like a pulse, electrons going up and down in tiny copper wires. The electrons flow in the antenna, which then cause perturbations in the electromagnetic field, which then radiates out, creating radio waves. So when you click send, it makes electrons dance in a certain way that makes radio waves that have encrypted the message in a certain movement. These radio waves radiate out towards the cell tower. The receiving antenna at the cell tower reads the radio waves pulse and replicates the electron dance that the phone produced. This electron movement is a set of electric impulses in tiny wires, which are then decoded in the cell tower. This decoded information is then carried through cables underground for thousands of miles until it reaches the cell tower close to the phone you sent the message to. The cell tower then receives the decoded message and releases radio waves that were the same as the one sent by your phone until it reaches the phone being sent to. The cell tower sends it in all directions as an encrypted message that only can receive and decode. The reason why cables are still being used is because radio waves can be blocked or have interference, messing up the messages being sent. The cell tower knows what phone is sending to what because each code has a unique identity that only is with the device. Also, the phones sending messages follow a protocol to send the messages to the tower at different times, or different frequencies, or different locations, or using different codes altogether. Ultrasound. The human ear can hear 20 Hz to around 20,000 Hz. Sounds below 20 Hz is called infrasound, and frequencies higher are called ultrasound. An ultrasound is a medical device that can see damages inside of humans. This device is called a transducer. You place it up to the skin, and it takes electrical energy and turns it into sound energy. It sends out sounds in forms of pulses. Anytime there's a difference in the medium, the sound will be reflected back to the transducer. Due to the machine knowing the speed of sound and the distance the wave traveled before being reflected, it is able to tell where the damage is inside and create an image of this difference in material. The sound pulse will keep traveling through the damaged tissue and reach the other side and repeat sending reflections back to create a full image of this damaged tissue. And this occurs all around it, so the ultrasound is able to get a full image of where this damaged tissue is. The reason why ultrasound is being used is for multiple reasons. First, it may be too noisy if it is in audible hearing range and may upset the patient. Second, ultrasound waves have a high frequency and low wavelengths. They correlate for the speed is wavelength time frequency. So the frequency gets higher, the wavelength must be shorter, because the speed is not determined by wavelengths or frequencies, but is affected by medium in which it travels and temperature in which it is traveling through. At a higher frequency and a low wavelength, it results in less diffraction, and less diffraction leads to a clearer image because the sound waves do not spread out as quickly as lower frequencies. Now last, solar. Turning sunlight into energy is a perfect way to gain energy. Sand must be converted to 99.999% pure silicon crystals to use in solar cells. Once a solar cell is made, it turns into a thin sheet called a silicon wafer. The silicon wafer is how a photovoltaic cell turns light into energy. The bonds in the materials cannot move, and when there is sufficient energy in the silicon wafer, the electrons move freely. When light strikes a solar cell, the electrons gain photon energy and will be free to move. The movement of electrons is random. To make all the electrons travel in one direction, a driving force is necessary. An easy way to create this is allow a p-n junction. This is the process of having another solar cell that has boron with three valence electrons that will be added with pure silicon. There will be a hole for each electron. This is called p-type doping. If these two materials join together, the free electrons close to the material will go into the hole. Due to this, a depletion region is formed, where there are no holes and no electrons. Due to the electron migration, the side with the free electrons will be slightly positive due to the electron migration, and the p side will become negatively charged. An electric field is formed from this, which is a necessary driving force. When photons hit the n-type side, there is sufficient energy for electrons and hole pairs to enter the depletion region. The electric field in the depletion region drives the electrons and holes out, leading the electrons to go back to their original spot, while the holes go back to their original atom. The concentration of electrons to holes becomes so high that a potential difference will develop between them. If there is any load that is attached between them, electrons will start flowing through the load. This leads to the solar cell continuously giving direct current. In a solar panel, the N type is layered on top of the P type of a cell to increase the performance of the cell. Okay, structure of the solar cell. A single PV cell produces only around 0.5 voltage. An increase of connection between the solar cell through positive and negative copper wires increases the current and voltage. Then there's a layer of EVA sheet behind and in front of the solar cell to protect it from shocks, vibrations, and humidity. Thank you for listening.